Thank you. Thank you very much. So thank you for the introduction, first of all. Hello to everyone. Good afternoon. I'm America Califano, a postdoc researcher from the University of Salerno. And today I'm going to show you some very preliminary results about the fatigue crack growth behavior of 17.4 pH stainless steel specimens obtained both by additive manufacturing and traditional manufacturing techniques. Well, we all know the high potential of additive manufacturing techniques, especially when dealing with metals, so when dealing with techniques like the laser powder bed fusion ones, because they allow to produce any kind of complex shape. However, the performance, mechanical performance of the manufactured metals are influenced by many factors like residual stresses, porosities, the crack orientation, or the environmental conditions. So there is still the need of deepening the knowledge about the mechanical behavior of metals obtained with these innovative techniques. And especially there's the need of deepening the knowledge about the fatigue behavior and the crack propagation. That's why in this framework, the aim of this work is comparing the crack growth behavior of stainless steel CT specimens obtained by additive manufacturing with the wrought stainless steel CT specimens. The activities were based on few main steps. So first of all, there was the manufacturing of the stainless steel plates by means of, on one hand, selective laser melting technique, and on the other hand, the classic, the traditional rolling technique. The CT specimens were then extracted and prepared. They were subjected to metallographic analysis. At least the additive manufactured specimens were subjected to metallographic analysis. Then the specimens were equipped, instrumented, and finally subjected to crack propagation tests, and the obtained results were compared. So considering on one hand the additive manufactured stainless steel, on the right here you can see a picture of the used powder, and in the table you can see the printing parameters. At the end of the printing phase, a rectangular plate with a thickness of 8 millimeters was obtained. Then the plate was milled and finally grinded, and a final thickness of 6.65 millimeters was reached. Here you can see schematization of the plate, from which 10 specimens were extracted by means of the electric discharge machining method. And in particular, one specimen was used for the experimental machine setup. One specimen was used for carrying out metallographic analysis, and the remaining 8 were used and will be used for carrying out experiments about crack growth, both in air and in corrosive environment. In this work, so in this contribution, I will show the results for specimens number 2 and number 5 that are, as you can see, characterized by notches that are along 2 different directions. So concerning the metallographic analysis that were carried out on one of the specimens, if we bear in mind that the building direction was direction Z, as shown here in the slide, and if we take a look at the macrographs, it is quite clear that the YZ and the XZ planes, so the planes that are along the building direction, are characterized by very thin and slender grains that are easily visible from the macrographs. So they share similar behavior, while the XY plane that is orthogonal to the building direction has more homogeneous macrostructure. On the other end, considering the wrought material, at the end of the rolling phase, a rectangular plate was obtained with a thickness of 12 millimeters. It was milled and grinded in order to obtain a final thickness of 6.65 millimeters as well. Here you can see a schematization of the plate from which 2 slices were cut out, and from each slice 6 specimens were extracted by means of the electric discharge machining method. And the specimens are identified with 2 letters and a number. The 2 letters stands for the direction of the notch. So if the notch is orthogonal to the rolling direction that is shown here in the slide, the designation is TL followed by a number. Otherwise, if the notch and therefore the crack is parallel to the rolling direction, the designation is LT followed by a number. In this contribution, I will show you the results for specimens TL 1 and 2 and LT 1 and 2 that have been subjected to fatigue tests. As a matter of fact, here you can see a schematic of the CT specimen with the dimensions expressed in millimeters, while on the right, a simplified schematization of an instrumented specimen. Each CT specimen was instrumented with 2 crack gauges, characterized by 20 filaments each, and with a distance of 0.254 millimeters between 2 adjacent filaments. And then a back face strain gauge was glued as well on the face that is opposite of the face on which the notch was introduced. These specimens were subjected to tension-tension fatigue tests with a maximum applied load of 5,500 newtons and a frequency of 5 Hertz with a pre-crack of 1.3 millimeters. And fatigue tests were carried out using the Instron 8502 machine with a loading cell of 20 kilonewtons belonging to the machine design lab of the University of Salerno. And here on the right, you can see a picture of an additive manufactured CT specimen at the end of the experimental test. The data that were collected using the back face strain gauge and the crack gauges were used to were compared and calibrated using the Newman-Johnston compliance equation for back face strain, as my colleague Dr. Giannella already showed in his presentation. So using these equations, it is possible to calibrate the measures and to compute the Young modulus for the considered material. And from calibration, it was found out that the Young modulus is 165,000 megapascals for the additively manufactured stainless steel. And in addition, the Newman-Johnston equation allows to monitor the crack length against the number of cycles. The same procedure was carried out even for the wrought material. And in this case, a Young modulus of 195,000 megapascals was found. So there's a difference of about 30,000 megapascals between the Young modulus of the 2 materials. And again, here you can see in the 2 pictures, in the two plots, the curves of the crack length against the number of cycles for the LT1 and TL1 specimens. At this point, we can take a look at the crack growth curves after pre-cracking for the 2 different sets of specimens. So for the additively manufactured CT specimens that are shown here in this slide, so we can see that the 2 curves for specimen number 2 and number 5 are almost completely overlapping, and even in terms of a number of cycles to failure, the specimens share a similar behavior. So there is no influence in this case of the crack orientation on the fatigue life, and a similar behavior can be found even in the wrought material. So if we take a look at the 4 crack growth curves after pre-cracking, they share similar behavior, and the number of cycles to failure are quite similar to each other. In the end, if we compare the results for the 2 sets of specimens, we can see that there is a clear difference, a clear different crack growth behavior. And this difference has to be found in the fact that the 2 materials have different microstructures, and that the wrought material was in simple annealing conditions, so it was not post-treated. And therefore, we can even see that there is a clear difference in the number of cycles to failure if we compare the 2 sets of tested specimens. So in conclusion, I showed you some very preliminary evaluations about the crack growth behavior of both additive manufactured and wrought stainless steel specimens. In particular, CT specimens were equipped with the back face strain gauge and 2 crack gauges and subjected to fatigue tests. And the data collected by the sensors were calibrated by means of the Newman-Johnson back face equation in order to find the Young modulus of the two materials. On the additive manufactured stainless steel metallographic analysis were carried out, and they showed different surface characteristics based on the considered plane. Then the crack growth curves have been showed for each material, and they are almost completely overlapping for the two different sets of specimens. The difference between the two sets of curves stands in the fact that the materials do not have the same microstructure, and the wrought material was not post-treated, while the additive manufacturing materials during the printing phase is sort of subjected to a thermal treatment, so a sort of hardening. And finally, future activities will deal with carrying out experiments on the wrought materials subjected to different thermal treatments in order to better compare the results with the additive manufactured stainless steel. And the further experiments will be, and actually they are in progress, as my colleague showed in his previous presentation, in a corrosive environment, so especially in seawater, in order to investigate the stress corrosion cracking phenomenon. And with this, I finished, and I really thank you for your attention.
Thank you.
Thank you.
Thank you for the presentation. Is there any question from the audience? No? Maybe I have one.
Yes.
Maybe I missed the information. Both the material were heat treated. The material, I mean, wrought and additively manufactured material.
The wrought material was not post-treated, heat treated.
But the AM1, yes.
No, it was not. The AM1 was not treated as well. But as there is a clear difference between the crack growth curves, we found the reason in the fact that the high temperatures reached during the printing phase may result in a sort of hardening of the material.
Okay.